right, so there's a lot going on this sheet, and I'm probably going to use some blank sheets as we go along to try to do it in pieces. But this is, as I said, a lot of the stuff we're getting tonight is just information about functions. And in this case, a lot of information about graphs of functions and how to sort of analyze graphs of functions. So there's a lot on this page. I'm aware of that. But first, before we look at all this stuff I've written down here, let's just look at the graph itself. So first of all, do we all agree that that graph is going to pass the vertical line test? So it is the graph of a function. Do y'all agree? So it is a function, and I'm going to give it a name. I'm going to call it function f. Okay. So we're going to start here at the top. I want to make sure y'all know how to do this. By the way, I've labeled some of the points on this graph, but I haven't labeled all of them. So remember, you know, like for instance, there's a point here and it's got an X and Y coordinate. You know, maybe X is -1 and Y is -2 there or something like that. I haven't labeled all the points. I've just labeled some of the ones that are kind of relevant to what we need to look at here. So, okay. Look at that graph, and that graph is a graph of the function f, and tell me what f of -3 is equal to. Say it again. 2? I agree. F of -3 is 2. So what is that asking us then? When it says f of -3, what's it actually asking? It's saying if your x value is -3, what's the y value that goes with it? Remember, f of -3 literally just means the y value if x is -3. So you just look at this graph and find the ordered pair whose x coordinate is -3, the y coordinate that goes with it, 2, that's f of -3. Everybody see that? So we can read functional values off of a graph. What's f of 5? 3. And what's f of 0? -4. Because we've got the point where whose x coordinate is 0, the y coordinate that goes with it is -4. Okay, domain and range. This is one that is often tricky for students. I want to make darn sure that we're clear what's going on here. Here's the most common wrong answer I get when I ask what is the domain of this function. The most common wrong answer I get is that the domain is the set of numbers -5, -3, -2, 0, 3, and 5. And that's the domain. Why is that totally incorrect? See, I agree that every one of those numbers are in the domain, but that's just a tiny piece of the domain. Is -4.999 in the domain? It is, because somewhere right in here is a point on that graph. Somewhere right in there is a point on that graph whose x coordinate's -4.999. Do y'all agree? And you know, 1 is in the domain because here's where x is 1, and there's a point on the graph whose x coordinate is 1. The domain of this thing is going to be every number. Remember, that's the set of x values. So from where x is -5 all the way up to here where x is +5, do you agree that no matter what number you choose between -5 and 5, somewhere there is a point on this graph that has that value for its x coordinate? Do y'all see that? Like if you have some number between -5 and 5 that you think is not in the domain, let's say you think -0.7 is not in the domain. Well, here's -1. Somewhere right about there is -0.7. Do y'all agree? And if I look down from there, that is a point that has -0.7 as its x coordinate. Do y'all agree? So this graph is connected. It's a solid line or whatever curve. Then every number between -5 and 5 is in the domain. To say that, we're going to use interval notation. Now, in this case, I need square brackets on both ends of that. Do y'all see why? Because remember, the square bracket means -5 is in the domain, and it is, because there's a point on the graph that has -5 for its x coordinate. And the square bracket on this end means 5 itself is in the domain, and it is, because there's a point that has 5 as its x coordinate, and that point is on the graph. You can see that nothing bigger than 5 is in the domain because that's an end point. The graph doesn't keep going. And there's nothing smaller than -5 in the domain, because while this number line keeps going out here to -6, -7, and so on, well, -6, for example, isn't in the domain because you can't look down and find a point on the graph from there. Does everybody see that? So that's our domain. What is the range? Remember, the range is the set of all the y coordinates. In this case, it's going to be the set of all the y coordinates that show up anywhere as y coordinates of ordered pairs of points on this graph. So what's the range? I agree. It's -4 to 3. -4, that's the y coordinate of this point. 3 is the y coordinate of this point. And do you see that if you look along the y-axis from -4 up to 3, first of all, there is no y value smaller than -4 that ever shows up on the graph, right? And there's no y value bigger than 3 that ever shows up on the graph. But every number between -4 and 3 shows up at least once as a y coordinate of some point on the graph. Do y'all see that? So the range goes from -4 to 3. Now let me ask you a question. What if this graph, let me make a slight change to it. What if this graph didn't stop here? What if it kept going and there was an arrow on the end? What would the domain be now? Yeah, it's not -5 just up to 5 anymore. Now it goes from -5 all the way on to positive infinity, because remember, this x-axis goes forever. And if there was an arrow here, that means as you go along this x-axis, no matter how big a value you picked, if you looked up far enough, you would eventually see, I can't write on the desk or I'd get in trouble because this is a permanent marker, but you would see that eventually there's a point on the graph. Oh, you can't even see what I'm doing there. If this thing keeps going forever, then no matter where I get out here on the x-axis, if I look up far enough, there's going to be a point on the graph with that value as its x coordinate. So if there were an arrow here, the domain would go from -5 to infinity. And if there were an arrow here, do you agree that the range would go from -4 to infinity, right? Because the y values would keep going up forever as well. Everybody see that? And of course, if there were arrows on both ends of the graph, both the domain and range would go from -infinity to positive infinity. In other words, that include all real numbers. Okay. Now, that's not what we had, but I want y'all to see that if we did, that's what we'd be dealing with. Okay, x-intercepts. X-intercepts are simply where the graph hits the x-axis. So where does the graph hit the x-axis? Well, I didn't label this point, but the graph clearly hits the x-axis at that point, right? What is that point? Isn't that the point where x is -4 and y is 0? Everybody see that? No. Well, there's -1, -2, -3, -4, -5. Everybody see? And so that's an x-intercept. Here's an x-intercept at -2, 0. and here's an x-intercept at 3, 0. So there are 3 different x-intercepts here. Here's how you should write that. Don't write, sometimes students do this. They say, okay, the x-intercepts are -4, 0, -2, 0, and 3, 0. That's not really wrong, but that's not how we want to write it. We're just going to write the x-intercepts are -4, -2, and 3. So the difference, or the 2 different ways of looking at it, and some of y'all may have been taught to write the x-intercepts this way. It's not that it's necessarily incorrect, but it is redundant. Because if it's an x-intercept, should I have to tell you what the y-coordinate is? Isn't the y-coordinate 0 at every point on the x-axis? So the way this book and this particular textbook that our course is based on, and the way that author views it, some of the ways he views things I don't think are the best ways, but this is a case where I think he's doing it the best way, because to make you write out the entire ordered pair for each of the x-intercepts doesn't really make sense, because if it's an x-intercept, we already know that the y coordinate is 0. So you just give the x values, you just give the values along the x-axis where the graph hits the x-axis, right? Similarly, for the y-intercept, what is the y-intercept? -4. I agree. And notice we're not going to say that the y-intercept is the point 0, -4, because again, you don't need to say that. If it's a y-intercept, we know the x-coordinate 0, the x-coordinate 0 at every point on the y-axis. Let me just say this about that. Like on the test, if I had this on the test and asked you for the x-intercepts and you told me this and you gave me the ordered pairs, I would not count off points. I would not count it wrong. But I will tell you that in the homework, when they ask you to give the x-intercepts, if you enter this, they're going to tell you it's wrong. And you're going to say, well, why is that wrong? Because it is -4, 0, -2, 0, and 3, 0. It's wrong because that's not what the computer's looking for, because this author prefers us to just give the x coordinate of those points where it hits the x-axis. Everybody with me? And the same for the y-intercept. Okay, so far, do y'all agree that this stuff we're doing, where we're looking at this graph and we're trying to sort of pick out information about it, some specific functional values? What is its domain? What is its range? What are the x and y-intercepts? That's all pretty straightforward, right? Like, I don't think there's anything too difficult there. Relative maxima. By the way, so let's talk a little bit about relative maxima and minima. So the term relative maxima, first of all, maxima is just the plural of maximum. So if you have more than one relative maximum, you wouldn't say relative maximums with an S, you would say relative maxima. So then the question is, what is a relative maximum? A relative maximum is a high point on the graph. That's like a real simple layman's way of saying it, and that doesn't tell us everything we need to know. But for right now, just intuitively, a relative maximum is a high point in a region of the graph. In other words, if I have a graph that looks like this, Julia was looking at some graph a minute ago that looked kind of like this in one of her homework problems. And I don't know, let's just say it looked like that. Or maybe it has arrows on the ends. She's looking at something like this. That point is a relative maximum point. And this point is a relative maximum point. Y'all see that? So if I had this instead, I should have done it like this. It's kind of like I'm giving you the finger. Sorry, I didn't mean for that to happen. This is the absolute maximum point. Do y'all agree? But that point, along with both of these points, those are all relative maxima. So relative maximum doesn't mean it's the highest point on the graph necessarily. It means it's the highest point in some region of the graph. So notice how if I look at this point, if I draw a little circle that includes that point along with some points to its left and right, this point is higher on the graph than any of those other points in that little region. Do y'all agree? Then it's a relative maximum point. It doesn't have to be the absolute highest point on the graph. It could be. This is also a relative maximum point, but it doesn't have to be. And by the way, just for the next thing we're going to look at, that point is a relative minimum point. And this point is a relative minimum point. Again, this probably is the well, first of all, there is no absolute lowest point on this graph. You see that? Because look, that keeps going down forever. But in this region of the graph, that's the lowest point. And in this region of the graph, that is the lowest point. Everybody see that? So, okay, back to our graph. -3, right here. Do y'all see that that is going to be a relative maximum point? That point where x is -3 and y is 2, that is a relative maximum point. Are there any other relative maximum points on this graph? Or is that the only one? Yeah, I was going to say, y'all probably think that 5,3 is a relative maximum point. This is important. It's actually not. And there's a reason why it's not. When I say that a relative maximum point is the highest point in some region of the graph, I kind of cheated because I didn't exactly explain what I mean by region of the graph. But when I say that this point is a relative maximum point, to be a relative maximum point, it has to be higher on the graph. In other words, have a bigger y value, right? Its height on the graph is literally its y value. It has to be the highest point on the graph in a region around this point. And here's what we mean by region. That region has to include the point itself, the one that in question that you think is the relative maximum. It has to include at least one point to its immediate left and at least one point on the graph to its immediate right. So I can make that region really small, but it has to include the point in question that we think is going to be the relative maximum, and it has to include at least one point to its immediate left and at least one point to its immediate right, and it has to be the highest of all those points. And so what went wrong here, let me go back to this other one. What went wrong here is this is the highest point, but the problem is we can definitely say it's higher than points to its immediate left on the right, points to its immediate left on the graph. But is it higher on the graph than points to its immediate right? No, because there are no points to its immediate right. Do y'all see that? And look, what if this graph did, I wish I hadn't crossed through that now, because remember what I said earlier, this graph stops here. So we can't make any analysis of what happens after this point. What if the graph did keep going? Well, either it's going to keep going like this, in which case, do you agree that we would never think of that as a relative maximum point because the points just keep going higher and higher as they go past it? Or maybe if it continued, maybe it would do like this, where that would be a relative maximum. But you can't determine whether it is or not unless it's got points on both sides of it. So the moral of the story is, as far as what y'all need to know or how that's going to impact y'all, if a graph has an end point, that end point cannot be a relative maximum or relative minimum. Because to be a relative maximum, it's got to have points on both sides of that point. And the point that is the relative maximum has to be higher than the points on its left and its right. Y'all see that? Okay. And so once you see that, do you agree then that there's also only one relative minimum on this graph? And what is it? What's the relative minimum point? 0, -4. I agree. That is the lowest point in that region of the graph. This is not a relative minimum point because we don't have points on both sides of it to be able to determine that. Everybody with me? So pretty straightforward. Let me talk just a drop more about relative minimum, then we'll talk about this increasing and decreasing business. Okay, let's say that our graph looks something like this. And I'm just going to guesstimate what some of these points might be. So let's say this is, so maybe that's the point -2, 3, and maybe this is the point, what's that look like? I don't know. We'll call it +2, 3, and maybe this one is, maybe this one is 4, -2. Okay. Does everybody agree that 4, -2 is a relative minimum point? And do y'all agree that that's the only relative minimum point? Are there any relative maximum points? These two? They're actually not. Why are they not?
Because the middle doesn't go down.
Right. The problem is, remember, to be a relative maximum point, there have to be points on both sides of it. There are, but it has to be higher than the points to its immediate left and its immediate right. So like this can't be a relative maximum because it is higher on the graph than points to its immediate left, but it's the same height as points to its immediate right. And so you know what's going to happen. If you call -2, 3 a relative maximum, then this point here, whatever that point is, it's going to cry foul because it's going to say, I'm just as high up on the graph as that point and I'm right next to it. Why don't I get to be a relative maximum, right? So the point is, you can't have an end point as a relative maximum or minimum because you've got to have points on both sides of that point. But because the points on both sides of that point have to be, for a relative maximum, have to be lower than the point that you claim is a relative maximum, then if you have a horizontal line segment as part of your graph, then the endpoints of that little horizontal line segment can't be a relative maximum or minimum either. Y'all see that? Because on one side of it, you've got points that are the same height. Everybody with me there? Okay, so that's pretty much what we got to know about the whole relative maximum and minimum thing. So let's talk about increasing and decreasing. So this increasing and decreasing business, what we're looking for are intervals. Intervals, so immediately that should have you thinking interval notation, intervals on which the function is increasing or decreasing. So let's talk about what we mean by that. So when we look at this graph, I think everybody, and y'all look, try to ignore where I've been scribbling here, and let's kind of look at just the original graph from this endpoint to this endpoint. Okay, I think when y'all look at that, and I say on what intervals is this function increasing? When y'all look at the graph, this is just sort of intuitive. Does everybody agree that when you look at this graph, if you look at this little part of the graph, you would say that it's increasing? Like as you go from left to right, the graph is going up. That's increasing, right? And if you look at this part of the graph, from this y-intercept to the end here, again, as you go from left to right, as your X values go from smaller to bigger, right? The graph is going up from left to right, so it's increasing. And here in the middle, that area, you see the graph, the height of the graph as you go from left to right along the x-axis. If you look at what's happening with the graph, it's decreasing, right? So it's easy to look at the graph and know kind of intuitively, where is this function increasing? Here and here. Where is it decreasing? Here. The trick is, how do we communicate that? And so when they ask for intervals on which the function is increasing or decreasing, which is what they're asking for, they are looking for the interval of x values over which the y values are increasing, which means graphically, notice here, when my x value goes from -5 up to -3, as I go along the x-axis from left to right, from -5 up to -3, as my x values are going up, the y values are also increasing. Graphically, that literally means the graph is just rising from left to right as my x values go from -5 up to -3. Do y'all see that? It's the interval of x values they're asking for. When they say, give me an interval where the function is increasing, on this interval of x values from -5 to -3, the function, the value of y, is going up, right? But like I say, graphically, that just means as x goes through this interval of x equal -5 up to x equal 3, the graph is rising from left to right. So we are increasing on the interval from -5 to -3. It's the interval of x values, right? This is not an ordered pair, right? That's an ordered pair. This is an interval of numbers. It's an interval of x values. Everybody see that? It's a little part of the domain over which the graph is rising. Then when I get here to where x is -3, it starts decreasing. And from the time x is -3 all the way up until x is 0, from -3 all the way on to 0, from -3 on to 0, that function is decreasing. As x goes from -3, remember that's where x is 0 here, right? As x goes from -3 to 0, the graph is falling from left to right. So it's decreasing on the interval of x values from -3 to 0. Then it starts increasing again. Y'all see that? So there's another interval where it's increasing. It starts increasing again. Once you get to where x is 0, it starts increasing. And it's going to keep increasing all the way until you get to the end of the graph, which in this case is at 5, right? From x equals 0, because remember, this is an end point. Like if I'd had an arrow, if I had this arrow where it kept going up, it would be increasing from 0 all the way on to infinity. But I've got an end point, so the graph totally stops there. So it is increasing on the interval of x values from 0 to 5. Oh, sorry, increasing from 0 to 5. So it's increasing on the interval of x values from -5 to 3. As x goes from -5 up to -3, the graph is going up, which means, of course, the y values are increasing. Then when I get to -3, all the way up until x is 0, the graph is falling, it's decreasing. The y values are getting smaller. Once I get to where x is 0, it starts increasing again. It's going to do that all the way to the end of the graph, which in this case is at x equal 5. And so increasing from 0 to 5. Everybody see that? It's super easy. You just got to make sure you see what they're looking at, because a lot of times students will try to give me ordered pairs. They'll say it's increasing from -5, -2 to -3, 2. That's not an interval. That's not what they're asking for. they're asking for the interval of X values between those points, which is all the X values from -5 up to -3. Everybody see that?
Can you tell me why on the homework it wants different brackets?
That's actually a good question. So her question, for those of you who couldn't hear it, which probably most everybody, certainly at Paris and Sulphur Springs, she's asking why is it that sometimes they want these square brackets and sometimes they want round, like why did I use only rounded parents when I gave these intervals? And there's actually a real simple reason for that. I'm going to show it to you because I think it's good to know this. It'll help you understand why it works this way too. Let me draw a graph that's a little cleaner than that one. Let's say I've got something that looks like this.
You gotta pop up.
No idea what happened there. Okay. Let's say, let me just real quickly draw a rough sketch of a graph. And let's say it looks like this. So I'm putting arrows on the end of this one. And let's say that this point, I'm just guesstimating. Let's say it's maybe that's where X is -2 and Y is -3. And maybe this is where maybe this is where X is 4 and Y is 6 or something, roughly like that. Okay. First of all, do y'all agree that both the domain and range here are all real numbers? I got arrows on both ends, right? And
Mr. Norris,
one arrow's going up, which means the arrow on both ends. If it's a function, there are arrows on both ends. The domain has to be all real numbers. Say
Mr.
what?
Norris,
Yes.
are you recording?
Yes, I think.
Are you sure? I think we are not.
You are.
If I am
Well,
recording, do I win $100? No.
You'll have to just add it to our tab.
Good line. I am recording. Shockingly, I remembered.
Okay, we're just making sure because we were a little bit lost, so we're definitely all talking about having to just rewatch this ASAP.
Yeah, I am recording.
Thank you.
Okay. Do y'all agree that anytime there's arrows on both ends, if it's a function, the domain has to be all real numbers? Because it has to go out somehow in both directions to positive and negative infinity. Because if this ever started going straight up where the X value stopped, it wouldn't be a function. It'd fail the vertical line test. The range in this case is all real numbers from -infinity to infinity, but the range with arrows on both ends may or may not be -infinity to infinity, because if you look at, let me go back to this sloppy, terrible looking thing. If you look at that graph, do you agree here the domain is -infinity to infinity, but the range, let's say that's where Y is, I don't know, 6. The range here would be from -infinity up to and including 6. Do you agree? Because it's going down toward -infinity, but it never goes higher than 6. But if you've got one arrow going up and one arrow going down, then you know that the domain and range both have to be all real numbers. Okay, so out here's the direction of -infinity. Out here's the direction of positive infinity. Does everybody agree that -2, -3 is a relative minimum point? And 4,6 is a relative maximum point. While I'm on this and while I'm thinking about it, let me tell you something you're going to see in the homework about relative maxima and minima. And if I don't tell you this, it'll confuse you. In the homework, when the author asks in a homework problem for the relative maximum, like when I ask you, say what?
Oh, I think we have you back now. It was not connecting.
It wasn't connecting, but she thinks she has you back now.
Can you see my camera and hear me?
Yes.
Let me reload this session because it has a notification really quick.
Y'all think they're saying they do have my camera and my...
She said she's checking something real quick. But while I was doing the homework, it seems like the only time you would put it in parentheses would be for the infinity, and then the real number would be the bracket.
We're going to talk about that.
You're gonna have to say yes.
Okay, have you got
Can you hear
me?
me?
Yes.
Okay, we had to reload the session. Thank you.
Okay. All right. So look, we're looking at this graph. And I'm going to get to your question. Just hang with me.
Yeah.
But I thought of a couple other things I probably need to mention to y'all. So I'll get there. As the Donald would say, I'm doing the weave. Sorry. But everybody sees that the domain and range is all real numbers. Just to see another example of that. And everybody sees at this point, -2, -3 is a relative minimum point. When you see something like that on the test and you're asked to list any relative maxima or relative minima, for a relative minimum, I'm perfectly happy with you telling me that -2, -3 is the relative minimum point, because it is. But here's how the author expects you to do this in homework. When he asks for a relative minimum point, he'll ask the question in two parts, and y'all need to watch this because you're going to get really confused on a couple of homework problems if you don't. He'll say, where does the relative minimum occur? Where does the relative minimum occur? He is asking for the x coordinate of the relative minimum point. It occurs when x is -2. Then he will ask, what is the relative minimum? The relative minimum is -3. So when I'm asking for the relative minimum, I'm just expecting you to tell me the relative minimum point. He wants to know, when he says, where does the relative minimum occur? Remember, the minimum, the actual minimum is the actual height of the graph at that point. And at the relative minimum point, the height of the graph is -3. It's 3 units below sea level, right? So when he says, where does it occur? It happens at mile marker -2, the x coordinate, right? Well, what is the elevation at mile marker -2? It's -3. It's 3 miles or 3 feet below sea level or whatever that is, right? So just know that, and he'll do the same thing with the relative maximum. When I ask for the relative maximum, I'm just expecting you to tell me the relative maximum point is the point 4, 6. He's going to say, where does the relative maximum occur? At 4. What is the relative maximum? 6. Everybody with me? Okay. So on to the increasing, decreasing. Do y'all agree that this function is decreasing on the interval of x values from -infinity up to -2? It is decreasing. Let's make sure we see why that is. Remember, we're thinking about intervals of x values. Because this arrow says that this thing is falling from left to right forever, all the way back from the direction of -infinity, all the way up until I get to where x is 2, all along there, it's falling. Do y'all agree? It's decreasing. So it's decreasing on the interval from -infinity to -2. Now here's a question. Why didn't I write this instead? Why didn't I put a bracket around that -2? There is a reason. If I did put the bracket around -2, what am I saying? What I'm saying is it is decreasing at -2. In other words, I'm including -2 in this interval of x values over which the graph is falling. But is the graph falling at -2? At that point, is the graph falling? Is it? For it to be falling, it would have to keep going down after it passes -2, wouldn't it? But it doesn't. It never goes any lower than It is when x is -2. So it's not decreasing at -2. It's increasing at -1.99999, but it stopped, or at -2.00001, but it stops decreasing at -2. And then it starts increasing. At -2, it starts increasing. By the way, you can't say it's decreasing at -2 and then turn around and say it's increasing at -2. Do you agree? It turns out it's doing neither. And it's going to keep increasing up until x is 4. Now, when you get to 4, it starts decreasing again, right? And it's going to keep decreasing all the way on to, and be careful, somebody will want to say on to negative infinity because that's falling. No, it's the x-axis. It's increasing for every x value all the way on toward infinity. And so think of it this way. You're on the roller coaster at Six Flags. And you get on the roller coaster, whee, and so on. When you are here on the roller coaster, there's your little roller coaster. There's you, got your arms up, you know, and you're all excited and feeling so brave. Do you agree that right here on the roller coaster, your height is increasing, right? So let's say that right there, you are right where x is 2, then your height is increasing at x equal 2. When you get here to the very top of the roller coaster, there you are in your little car. There's you smiling. Got your arms up because it looks super cool and brave to hold your arms up. When you're at the very tip top of the roller coaster, is your height still increasing? No, then you are not increasing at 4, right? You're not increasing at 4. When you're at the very, very tip top, in that little instant of time, when you're at the very tip top of the roller coaster, is your height decreasing? In that instant, when you're at the very top of the roller coaster, it's not. You are balanced in space between going up and going down. You are between going up and going down. Do y'all agree? When you get to the very tip top of the roller coaster, your height is neither increasing nor decreasing. So your height is increasing from -2 to 4, but it's not increasing at 4. That's why you need a rounded parenth, not a square bracket, because your height's no longer increasing at 4. You are at the top of the mountain. You're not going any higher. But you also need a rounded parenth here when you say that it's decreasing from 4 on to infinity, because when you're at the very tip top of the roller coaster, your height is not decreasing either. It's about to be decreasing like really fast, all right? But it's not decreasing until you get past 4. Y'all see that? So when you give intervals where a function is increasing or intervals where a function is decreasing, you will never use a square bracket. Because whatever that x value is, where it stops decreasing, it's not decreasing at that x value. It also hadn't started increasing here yet either, right? So that's why you never use a square bracket anywhere where you're given intervals where you're increasing or decreasing. Remember, square bracket means that number is part of the set you're describing. The rounded parenth means that's the end point, but that point itself is not really in the set. Everything after that is, or if it's on the right end, everything before that is. Everybody with me?
So if it's the end point, you get the bracket, and if it's not an end point, you get the parenthesis.
If you are increasing at 4, you should put a rounded parent, a square bracket, but you're not increasing at 4. You're never going to be increasing. If you were increasing at 4, then the interval you would give here would have to have a number bigger than 4, right? Because if you were increasing at 4 and then you started decreasing, that would be the number where you stop increasing, not here. So that would never show up in the interval if you were still increasing at 4. It's always going to be Where you stop increasing, that's the number you're going to give here, right? And if you've stopped increasing, then you're not actually increasing at whatever that number is. So you always have a rounded parent. Does that make sense?
I guess I just don't understand you, because the homework, it's just.
You'll have to show me the question after class. Show me that question after class, and I'll tell you why either they're telling you to use a square bracket or rounded parent. But you have to remember, square bracket means that number is in the set. If I use a square bracket around 4, I would be claiming that this function is increasing at 4, but it's not. I have reached my maximum height at 4. I ain't going any higher. See what I'm saying? Okay. But anyway, yeah, we can definitely look at that after class. Let me see what else I feel like I need to get to. I can get to this because it's real quick and easy, and then that's probably going to run us out of time. But that's going to have us almost to the very end of 2.2. Not quite, but almost. Graph symmetry. This is an easy idea, so I think we got time to look at this. So this graph, now keep in mind that I'm drawing this freehand. I'm not using graph paper, and I'm not plotting it on a computer, but to the best of my ability. This graph has what we will call y-axis symmetry. And so you need to be able, when a graph exhibits y-axis symmetry, you need to be able to recognize that. So there's a few ways to think about y-axis symmetry. This graph, can y'all see that it's kind of a mirror image of itself on either side of the y-axis? Everybody see that? So think of it like that. It's like if you imagine that we lived in a two-dimensional world, like a flat world, then maybe this arc that's to the left of the y-axis might be some creature that lives in this two-dimensional world. And in a two-dimensional world, this y-axis, a mirror, would look like this y-axis. And do you agree, if that creature looked into that mirror, this is what it would see reflected back, what's on the other side of the y-axis? So y-axis symmetry is super simple. It is a mirror image of itself on either side of the y-axis. Here's another way to think of y-axis symmetry, and you'll have to watch this because I got to turn this paper. So I'm putting my fingers here along the y-axis. And if I were to just spin this graph, like imagine it was a top, and I just spun it on its axis, y'all look, there it is. If I spin it around, that looks like the exact same graph. Do y'all see that? If I spin it another half turn till I get back to the front, it looks the same, front or back. Because if I spin it 180 degrees, a half of a full turn around the y-axis, I get the same picture back. Y'all see that? So again, y-axis symmetry is super easy. It's a mirror image of itself on either side of the y-axis. But it is true that if it has y-axis symmetry, if you look at it from the front, or if you spin it around the y-axis till you're looking at it from the back, it looks the same. That's y-axis symmetry. Everybody with me? This one, do y'all agree that this is not y-axis symmetry? It's not a mirror image of itself. Now, if over here on this side, if it went up and down where this made kind of the letter M, that would be y-axis symmetry, right? But it's not. And you can see that if I were to spin it around the y-axis, notice, I'm going to use some technical math terms here, the hump is on the left and the dip is on the right. Technical math terms, hump on the left, dip on the right. If I spin it, that's not what we were looking at, because now the dip is on the left and the hump is on the right. That's backwards. Do y'all agree? By the way, sometimes you can have a graph that shows x-axis symmetry. Let me recycle this. Let's say this graph looked like this instead, like this was the x-axis and this was the y-axis. Do you agree that that one would have, if this were the x-axis, this would have x-axis symmetry, right? Imagine you were standing over a pool looking down into the water, and that's what you would see reflected back. It's a mirror image of itself on either side of the x-axis, or if you spun it around the x-axis, you get the same picture back. Why are we usually not interested in x-axis symmetry, do you think? Say again?
They're not symmetry unless they're on the y-axis, right?
What is the thing that we're looking at tonight that this is not an example of? A function, right? Any graph that has x-axis symmetry can't be a function because it's a mirror. Pretend like this is the x-axis. It's a mirror image of itself on either side of the x-axis. So if there's a point up here, well, that point, there has to be a mirror image point directly below the x-axis, that same distance. And obviously that fails the vertical line test. Do y'all agree? So there are graphs that have x-axis symmetry. We're not particularly interested in it because none of those are functions, right? Okay, so back to this. So we saw that if I spin it around the y-axis, hump on the left, dip on the right, now I've got dip on the left, hump on the right, so it doesn't have y-axis symmetry. If I spin it around the x-axis, I'm going to have the same problem, right? If I look for x-axis symmetry, the hump is on the left, the dip on the right. If I spin it around the x-axis, now the dip's on the left and the hump's on the right. Now here's something I could do. This is weird, but y'all check this out. What if I do, so remember, hump on the left, dip on the right. What if I spin it around the x-axis? That is not the same picture I had. What if I now take that thing that I spun around the x-axis, what if I spin it around the y-axis? Now I'm back to the hump on the left and the dip on the right. Y'all see that? That is called origin symmetry. And I'm going to show you why it's called origin symmetry. I know y'all are itching to get out of here, and I don't blame you. Here's why it's called origin symmetry. The easiest way to think about origin symmetry, or if you're looking at a graph and you're not sure if it has origin symmetry and you want to try to figure it out, see if you want to see if it has y-axis symmetry, probably easy just to say is it a mirror image of itself on either side of the y-axis. But you could also think about, okay, what if I turn the page over and looked at the graph like through the paper on the other side of the paper? Does it look the same from the back? Notice to do that, you're spinning this y-axis symmetry graph 180 degrees around the y-axis. The reason this kind of symmetry is called origin symmetry is because of this. Remember this point right here, 0, 0, that's the origin. So y'all seen those little pinwheels? You probably had one as a kid, you know, it's on the little stick and little thing and you blow on it and it spins around. Okay, imagine this is like a pinwheel and the pin is stuck right there in the origin. And if you spin it 180 degrees, that means I'm going to go from where this is the top until this is at the bottom. That's a half turn, 180 degrees. Look what happens when I do that. Hump on the left, dip on the right. I do that. There's 180 degrees. I'm right back to the hump on the left, dip on the right. Everybody see that? If you spin it 180 degrees around the origin, you get the same, you get a graph that appears exactly the same. Everybody see that? That is origin symmetry. Finally, last one. This doesn't have any symmetry. Or it certainly doesn't have y-axis or origin symmetry. Obviously, it doesn't have y-axis symmetry. Does everybody agree? Now, this is shaped kind of like that graph that had origin symmetry. So you might think it's got origin symmetry, but it doesn't, because notice the hump is on the left and the dip is on the right. But notice the dip is to the right of the y-axis, right? Y'all see that? If I spin it 180 degrees, the dip is now on the y-axis. It's not to the right of the y-axis. That's not the same picture that we started with. Do y'all see that? So you can kind of see for origin symmetry, look at the graph upside down. If it looks the same upside down as right side up, that's origin symmetry, right? But be careful, because here the hump's on the left and the dip is on the right. And if I turn it upside down, the hump is still on the left, the dip is on the right. But remember, that dip would have to be over here somewhere for it to have origin symmetry. Y'all see that? Okay, there's a couple other little topics in 2.2 that we're not going to get to tonight. Let me tell you what they are, just so if you're working on your 2.2 homework, you'll know when you've got to something like, okay, don't panic. We're going to talk about that next week. We're going to talk about even and odd functions. We haven't done that yet. So when they ask about even or odd functions, just know we haven't done that. And I think there might be one problem where they talk about piecewise functions, which is super easy, but we're not going to get to tonight. And then there might be one problem where they talk about the difference quotient. So even odd functions, that's in 2.2. Piecewise functions, that's in 2.2. And the difference quotient, that's in 2.2. We have not covered those yet. So if you get to those questions, which I think would be at the very end, maybe the last few in section 2.2, and you're not sure what to do with those, don't panic. Okay, we'll get to those at the beginning of class next week. I think probably true that next week I'll be bringing the practice test and I'll be sending it to Paris. I'm also in Sulphur Springs. Y'all also will get y'all's actual first test back next week. But I'll be sending those out because by the end of class next week, I think we'll literally be a couple of weeks away from a test. And, like I said, we don't quite finish all chapter 2 by then it won't quite all be on there, but I'll probably be bringing your practice test just so you can kind of begin to look at it. I think next week we will definitely get through 2.4, and that leaves us with 3 sections of chapter 2 to finish. So that's kind of where we're at. That is all I got. I'm going to stop recording just because these things get so long, man. It's a nightmare to try to process these things. So